again.
Like we
got some great things on the show today.
Kate, BYP here, studying the question of electrically small antennas, and to show you an article that every ham needs to read, because this sums up all of this question of hams trying to match electrically improper antennas. Not necessarily small, but the example I showed of using the 80-meter dipole on 40 is just the opposite. The 40-meter wavelength is much shorter. So that's a longer antenna, but still the mismatch is extreme. It's even worse in the short direction. Electrically short antennas, such as trying to use a 10-meter vertical on 80, which is ludicrous, becomes an electrically small question. And the universal approach to this is either to put attempt to put a matching network at the feed point to try to get some power into it, which I've shown in my videos doesn't work because it does nothing to change the fact that the antenna is no good, to put it plainly. Or doing more advanced things with the fields outside of the antennas with materials. And that's, if there's anything to be had, that's where it is. The problem with electrically small antennas, to put it simply, is that their lengths, their mechanical lengths, the length of a wire isn't long enough to fit the wavelength. And I can show with my dipoles, which are not really considered small, but what I'm doing with them is trying to completely optimize them for performance. Is that the reason they work so well is that the length is exactly, of each arm, exactly 90 electrical degrees long. Or in the question of propagation time, a quarter wave time long. And that's what does the magic of working 6,000 miles with half a watt. It's extreme efficiency. But this article looks at electrically small antennas which are, under one assumption, a 10th wavelength or less, such as a very short dipole and a very small loop, whose diameter is wavelength lambda over 10. For the dipole, the calculation is at 100 megahertz, a lambda or wavelength over 10 with 1 millimeter conductor has a feed point that is 1.96 ohms minus 1758, which implies capacitive. What that means is that the feed point's a dead short. And this is what I found with the 6-meter halo. If it wasn't coupled to something, it was a 10 ohm feed point, which is essentially a dead short. It's possible to build a matching network from 50 to 10. The values get weird for the components, but it's highly inefficient and it does not change the antenna in any way. It's a horrible solution to a problem that can't be solved. What's misleading here is the 1758. That's a big number. But see, 1758 ohms capacitive at the end of a transmission line isn't even there. That may be a spurious result from the software, NEC2, which has been thrown under the bus a long time ago by anyone in science. But 1758, there'll be no energy coupled into that with regard to a 50 ohm transmission line. So the transmission line is looking to a dead short. With the loop, and you'll notice nowhere here is a loop referred to as an antenna. And this evidences that fact. The loop in the portion of the paragraph under the figure 2, the feed point is 1.92, which is a dead short. But the loop is roughly 3.0 plus 800. 800 is an open circuit with regard to the end of the transmission line, but it proves that the loop is purely inductive. It is not an antenna. Because realize that the R value is not resistance. It is what represents emission into free space. So this loop is not being an antenna. It's just an inductor, and that's why they're called magnetic loops. That refers to the magnetic properties of inductors in their fields. But what hams need to see here is that the author goes on to figure a matching network scheme. Along the left, calculated theoretical with ideal components, and the one on the right, calculated with real components with Q of 100, which is good. But notice the radical difference between the values. 1.4 microhenry on the left, 1.42 on the right, but the huge difference in capacitance when using real components. And this illustrates a serious problem with trying to calculate a matching network when it's not resistive. This is what I've been hammering on. The feed point must be resistive. The output and the input of the matching network has to be resistive. It cannot be reactive, because when it's reactive, here's a train wreck that comes. But when calculating with the Q of real components, the author shows ideal inductors don't exist, practical Qs of 100, etc., etc. Since there are two inductors, the total additional resistance in the series with the antenna input is 17.58 ohms. That's in series with the, come on computer, that's in series with the 1.92 ohms of the antenna, and just by Ohm's law, all the energy is going to be dumped across the inductors. The author calculates that the losses due to Q just in the inductors in this system that someone's going to think is matched, the losses in the matching network just for the inductors is 21 dB. And this is on the order of what I'm seeing in on-air test between my absolutely perfectly matched antennas and those that are kludged up with matching networks. I'm seeing differences in signal reports on the order of 20 dB. It's extreme. The article goes on to say figure 3b, the real matching network with Q figured in, accommodates the additional loss. This shows how an empirically derived matching network, that means calculated, no, that means trial and error experimentation, can get results that are far different from the calculated values that don't account for losses. This illustrates my point of a matching network must have resistive ends. When it becomes reactive, like Terman says in Radio Engineers Handbook, the losses go up, and they go way up. 21 dB is turn out the lights, go off the air, go find something else to do, because the antenna system does not work. And this is a gross problem which hams run into when they try to use loops and find the feed points arcing. It's arcing because there's no energy being transferred into the loop because it's not an antenna. And the energy is being dissipated by arcing across the capacitor plates, and the inductors are spewing it off who knows where. Not an antenna, not useful. So there it is, published proof. It doesn't work. So forget the magic networks, forget the magic tuners, forget the magic balance. They don't work. KBYP out.